Hi everyone, today we're going to take the 2.5 notes, and this section is about continuity. So what makes a function continuous? Okay, so the actual definition in its words, all mathy and everything, is a function f is continuous at a number a if the limit as x approaches a of the function is equal to f of a, which means the function value. Now that's a little wordy. Basically all it means is if there's some curve, some function, whatever, and there's some number a on the x-axis, if I can draw that piece of the curve without lifting my pencil, the piece of the curve that's at a without lifting my pencil, then the function is continuous in that area. Now I've drawn, for example, right here, if this is -2 and this is +5, then and I'm calling this f of x, then I can say, look, I can draw this curve without ever lifting my pencil. So this function f of x is continuous over the interval -2 to 5. If there was any sort of break in it and I had to lift my pencil, then it wouldn't be continuous. And so an example of discontinuity is this. So if this is f of x and this is a, I would say f of x is continuous everywhere except where x equals a, because as I draw, I have to pick up my pencil, skip that open circle, and then move on. This would be called a removable discontinuity. A removable discontinuity is actually a hole in the graph. And if you remember, in functions where you have a common factor on the top and the bottom, you can cross them out. What becomes of that crossed out factor? You get a hole at that restriction at the -1, right? And so the fact that you're crossing them out, you are removing that set of factors. So a hole, we call it a removable discontinuity. Another type of discontinuity is around an asymptote, okay? So I can draw this piece of the curve, then there's nothing here. The asymptote is a domain restriction. And then I draw this piece. There's no way I can ever draw them without lifting my pencil. So this would be called asymptotic discontinuity. And then there's another one. It looks like this. For example, if this is a piecewise function, so what happens is I jump from some y value to a totally different y value, like a -2 to a +1 or something, and there's this gap here. That's called a jump discontinuity. And actually, anytime we talk about a jump discontinuity, I always think of the step function that looks like this, the greatest integer function, this one, y equals the greatest integer function of x. And so this function, which goes on forever this way and that way, has a whole bunch of discontinuities. It's discontinuous at 1, it's discontinuous at 2, it's discontinuous at 3. It has a whole bunch, infinitely many jump discontinuities. Okay, so those are the types. So now let me actually continue with a definition of continuity. So we say this is, the actual definition in math notation instead of just words. Definition of continuity, and this is super important that you know this one. You have to know it in and out. I'm going to quadruple star this thing. Okay, so if we already wrote a function f is continuous, cont continuous, at a if the limit x approaches a of f of x is equal to f of a. Okay, this means three things. One, you have to know this, you guys, I'm triple starring this, okay. One, f of a must be defined. There has to actually be a point at f of a, okay. Two, the limit as x approaches a of f of x must also exist, so it can't be DNE, okay. And then three, part one and part two have to equal each other, right? So when these two equal each other, you can conclude with this, okay? And if you conclude with this, that means your function is continuous. So if one of these two things doesn't hold true, you automatically say the function is not continuous. Okay, so let's do a few examples. Example one. Let's draw this one. Parabola with a hole, but then, we'll say this is 3, we'll say this is -1, and so we'll say this is 2. So, question is, this is f of x. Is f of x continuous at x equals 2? So, continuous at x equals 2 is the question. Well, the answer is no. How come it's no? Well, you have to go in order down this list. Does f of a exist? Does f of 2, so 1. Does f of 2 exist? Yes, f of 2 is -1. So guess what? Criteria 1 checks out. Criteria 2, it says, does the limit as x approaches 2, okay, we're talking a is 2 here, does it exist? Well, let's see. In order, what is true? What must be true in order for a limit to exist? Isn't it true that the limit incoming from the right and the incoming from the left must be equal? So if you approach 2 from the left side and you approach 2 from the right side, they both have a y value of 3. Guess what? Criteria 1 and criteria 2 worked out. They check out. That doesn't necessarily mean that the function is going to be continuous, because what's the third and most important criteria? Step 2 and step 1 have to have the same answer. They have to be equal, and they're not. So the limit as x approaches 2 of f of x is not equal to f of 2. Okay? Therefore, these 3 dots mean therefore, f of x is not continuous at x equals 2. So this is the sentence we're looking for. Okay, let's do another example. Example 2. How about this one? If I have a function, whatever, this is 1. Oops, I forgot the open circle there. And this is 1. Okay, so question, continuous at x equals 1? Well, let's see. Let's go down the list. Does f of 1, is f of 1 defined? Does it exist? Is there an f of 1? F of 1, well, there's a hole there. It's not defined. So this whole argument stops. You just stop. You answer the question. You say no. F of x is not continuous at x equals 1. There's always a because, and then you say because f of 1 is undefined. There's no point there. Okay, so this is our answer. All right, let's do another one. Example 3. How about this one? Let's call this 1 again. So, do we have continuity at x equals 1? Yes or no? Well, let's go down the list. 1, is f of 1 defined? If this is our a value, so is f of 1 defined? Let's see. Let's call that negative 1 and 1. Yes, there is a point there. I know there's no point there, but there's a point there. So that's equal to negative 1. So criteria 1 checks out. Criteria 2 says the limit as x approaches 1 has to exist. So let's see what the limit as x approaches 1 is. Remember, in order to figure out what the limit is, you have to approach x equals 1 from the left and the right side and see if they're equal. So as I'm doing this, you know what? The incoming limit from the left is negative 1, and the limit incoming from the right is 1, is DNE. So we don't even have to go to the third step. Our answer is no. F of x is not continuous at x equals 1. We need a because, and then you state the reason that didn't check out. Because the limit as x approaches 1 of f of x does not exist, okay? Your because will be one of the three reasons. It's either going to be this one, or the third one, okay? Let's see. Oh, I have a really good example. So example 4. How about f of x, let me give you a piecewise, is x squared minus x minus 2 over x minus 2. If x cannot equal 2, this domain restriction should not be a shocker because look at the denominator. And then I've got 1 if x is equal to 2. So I'm not going to know if this is continuous or not until I kind of get a feel for the problem. First of all, if you look at this rational function, I'm going to rewrite it over here. That top part is totally factorable into x minus 2 and x plus 1. Okay? If you remove, literally I'm using that word on purpose, remove x minus 2, this graph is going to have a hole in it at x equals 2. How do you get the y-coordinate? Remember, you plug in that restriction, the 2, into the reduced equation. So 2 plus 1 is 3. There is a hole at 2, 3. So if I go to the graph, my reduced equation is x plus 1, which is a nice little line. It's linear. Y-intercept 1, slope of 1, so it looks like this, okay? Before I connect those dots and make a line, I'm going to put a hole at 2, 3. 2, 3. And then I'm going to create the line, okay? And then, so I've graphed that portion. Then I'm going to graph this one. It says f of x equals 1, so y equals 1 if x equals 2. You guys, this is just a point, right? This is a point with coordinates 2, 1. So 2, 1. Look at our graph. Do you think it's continuous at x equals 2? I think not. Why is it not continuous at x equals 2? So continuous at x equals 2 is the question? No. What's the because? Well, let's go down the list. The first one is, does f of 2 exist? Oh, it sure does. F of 2 is equal to 1. See? Okay, so that first criteria checks out. What's the second one? Does the limit as x approaches 2 exist? Let's see. Incoming from the left, incoming from the right, towards 2. Looks like the limit is 3. So the limit exists. The issue is criteria 4, because the function value f of 2, which was equal to 1, was not equal to the limit as x approaches 2. Okay? The limit was 3. The function value was 1. Okay. Really quickly, I want to address one-sided continuity. So one-sided continuity, okay, is like this. The best way I know how to explain that is to draw a piecewise. Let's see, let's go open circle and then like that. Okay, and let's call this x equals 2. So I'm going to ask you, and this is f of x, f of x continuous at x equals 2 from the left? One-sided continuity. That means approach x equals 2 incoming from the left. Stop. If there is an open circle there when you get there, the answer is no. If this had been filled in, the answer would have been yes. So it's honestly a difference between is the circle open or closed. So now, same question. Is f of x continuous at x equals 2 from the right? Okay, so I'm going to approach x equals 2 incoming from the right. Stop. If the circle is closed, the answer is yes. Okay, the next thing I want to address is a theorem. Okay, so if f and g are continuous functions, continuous at x equals a, and c is a constant, then these are continuous also. Ready? The sum of the two functions will be continuous. The difference of the two functions will be continuous. The product will be continuous. The quotient will be as long as g cannot equal 0. A constant times each of the functions is continuous. Okay? So basically, if you start with two continuous functions, if you add them, subtract them, multiply them, divide them, or multiply either one by a constant, their result will also be continuous. All right. So these functions are continuous wherever they have a domain. Wherever they are not restricted, they are continuous. Trig functions, exponential functions, rational functions, root functions, inverse trig functions, logarithmic functions. And the most important one, polynomials, because they are smooth and what? Continuous. That's right. So these functions are just automatically continuous wherever they have a domain. Notice I left out piecewise. Not piecewise necessarily. Because if I have a function that looks like this, watch. Okay. What's the domain of this function? Domain. Everything until this x and then everything after this x value. Let's say it's -1. Is -1 defined? Yes, the domain is -infinity to infinity. So everything, the domain is all real numbers. But is it continuous over this entire domain? Nope, it's not. It has a jump discontinuity. So these, wherever they have a domain, will be continuous. Sometimes piecewise functions are not. Okay. One last thing that I have to talk to you about is the intermediate value theorem. Okay. For short, we call it IVT. And it says, suppose that f is continuous on the closed interval. Closed means brackets, not parentheses, so you're including the a and the b. and let n be any number between f of a and f of b, where f of a doesn't equal f of b. Okay, then there exists a number c in the interval a to b such that f of c is equal to that number n. Basically, here's what we're doing. We're saying there's an a and a b. There's some function, f of a, this is a comma f of a, this is b comma f of b. Well, if f of a doesn't equal f of b, this is f of b, this is f of a. These y values are not the same. And you notice that the function is continuous. Along the way, there's going to be a root, okay? Or there's going to be a positive 1 or a negative 1. If this is negative 3 and this is 3, along the way, there's going to be a y value between those two end y values, okay? There's 4 steps in this problem. 1, you have to show f of a does not equal f of b. 2, you have to show f of x is continuous. 3, you have to show n is between f of a and f of b. And then 4, you have to conclude with the statement, there exists a number c in the interval a to b such that f of c is equal to n. Okay, I'm going to save an example of this for in class. It's easier to explain when we're talking to each other. But for now, that'll be the end of the notes.